Good morning, class, and welcome to this lesson on Magnetism 10, magnetic flux. Today, we will be able to describe magnetic flux and how each component affects the flux. So, what is magnetic flux? Sounds kind of complicated, but it has a pretty simple definition. Magnetic flux is the amount of magnetic field lines, the amount of magnetic field lines that pass through a given area. The amount of magnetic field lines that pass through a given area. Okay, and the picture to my left here is a perfect example. We have two surfaces, we have two areas here, and we have field lines going through this one, and we have field lines going through this one. And what we can gather from this picture is that this picture is three times the amount of flux letter A does over letter B, because as we can see here, there's 9 arrows here, and there's only 3 here. So flux is the amount of magnetic field lines that pass through a given area. The amount of field lines that pass through a given area. Now, I just want to point out one thing just to be clear. There is no such thing. There is no such thing as field lines, okay? There is no such thing as field lines. Field lines are a model. They are a model we use as people to understand what magnetism is. By drawing 9 lines here and 3 lines here, this tells me as a person that this field is 9 times as strong. But it's not like if we look at this space in between here, if we look at this space in between these arrows, this space has a magnetic field there. Because we didn't draw an arrow there doesn't mean anything. The arrow is supposed to tell me the strength of the magnetic field, and it tells me the direction of the magnetic field. So more arrows mean more strength, and then the arrowhead tells me the direction. So there's really no such thing as magnetic field lines, but they're just a model for us to use, okay? So the flux passing through these areas is consistent over the whole surface. It is not just in these 3 specific spots, okay? So if we go back to our last video, if we think about what we learned about in our last video, we talked about a changing magnetic field. We talked about a changing magnetic field induces a current. So B, a changing magnetic field induces a current. We learned that from this picture right here. We learned that changing the area induces a current. Okay? And we learned that changing the angle induces a current. Well, the formula for magnetic flux is going to be given by the symbol phi. This is going to equal the magnetic field times the area times the cosine of the angle between them times the cosine of the angle between them. So we have magnetic field times the area times the cosine of the angle between them. So we talked about an induced current before. An induced current happens when the flux changes, because flux takes into consideration the magnetic field, the area, and the angle between those two surfaces. There's one thing I want to point out that a lot of students get messed up on. This angle right here, this angle is the angle between the field lines. It is the angle between the field lines and the normal to the surface. It is the angle between the field lines and the normal to the surface. So when we look at this surface right here, this line is the normal. It is perpendicular to this surface. So in this situation, the angle is 0 degrees because there is no angle between these field lines and this normal right here. So the cosine of 0 is 1. So we get maximum flux. We get maximum flux at 0 degrees. Notice here this is a 60-degree angle between the normal and the magnetic field lines, and this is a 90-degree angle between the normal and the magnetic field lines. At 90 degrees, we have 0 flux. We have 0 flux because no field lines are passing through this surface, through this area. Okay, so the area in this situation would be 0 as well. Well, that this is 0. This has an area, but no field lines are passing through that area. Okay, that's why we have the angle there. So something a lot of students get confused. They see an angle, and you have to make sure you're looking at the right angle, not the 90-degree right angle, but the correct angle. Okay, and so we have a formula for flux. Excuse me. Well, our formula for flux, we already went over this, equals BA cosine of the angle between them. This is just a number that doesn't really count. B is Teslas, A is area, meter squared. This is our new unit. This is the breakdown of the new unit, Tesla's meter squared, and this unit is known as a Weber. WB, WEBER. Okay. This was named after Wilhelm Weber. Wilhelm Weber. Okay, so this is going to be one of our new units, the Weber, based off BA cosine theta. So if any of the flux changes, if any part of the flux changes, whether it's magnetic field, area, or angle between the normal and the magnetic field lines, then we have an induced current. And we're going to start talking about that induced current in our next videos.